Good evening, everyone, and welcome to the Lifelong Learning webinar, Melting Giants. I'm Ruth Candler, Associate Director of Lifelong Learning at Washington and Lee, and tonight we're joined by two experts in their respective fields. First, we have Dave Harbour, Professor of Earth and Environmental Geoscience here at Washington and Lee. And alongside Dave is Mike Jackson, a seasoned naturalist and Lindblad National Geographic Expedition leader. I hope you've had a chance to familiarize yourself with their bios. To kick off our session tonight, Professor Harbour will provide a scientific overview of ice melt, shedding light on the underlying processes and implications for our planet. Following his presentation, Mike will share his firsthand observations of Antarctica's rapidly changing landscape, offering invaluable insights into the broader impacts of these transformations. After Mike's presentation, we'll transition to a question and answer segment. To begin, our speakers will pose questions to each other, and then we'll open the floor to your questions. Please use the Q&A tab at the bottom of your screen to submit your questions at any time throughout the webinar. Once we open the floor to audience participation, I'll be delighted to pose your questions to our panelists. Thanks again for joining us tonight, and Dave, the floor is yours.
Thank you, Ruth. See if I can get this correct. All right. Are you seeing the Earth?
We are.
Great. Are you now seeing the slideshow?
Seeing a web browser.
Oh, how about that?
There we go.
So thank you very much for the invitation to talk a little bit. I'm a geomorphologist. I have taught glacial geology, so I know a little bit about it, and I've been on a few in Iceland and other places. So I'm not an expert, but I have learned a lot in the last few weeks about Antarctica. So here's where we're going tonight. I'm going to be talking about the tectonics of Antarctica, how it got there, the development of its two ice sheets. The East Antarctica ice sheet is the big one, okay? Most of the eastern United States, and the West Antarctica ice sheet is a smaller marine ice sheet that formed later. I'll give you a little introduction to glacial movement, the glacial mass balance, the comings and goings over time. And then I'll talk in detail about the instability of marine ice sheets and how they can catastrophically collapse. And then lastly, I'll talk a little bit about sea level. So if we go back in geologic time, Antarctica wasn't glaciated. So if we go back 50 million years ago, it wasn't glaciated, but starting 34 million years ago, it was glaciated. And part of that is global climate related. And the temperature of the Earth has been cooling for the last 50 million years. Part of that is due to the erosion of sediment off of newly created mountains, and the weathering of those rocks sucks CO2 out of the atmosphere. And so the Earth has been cooling off. Another part of it, however, is oceanic currents. And let me see if I can switch back to the globe here. And if we go back 90 million years ago or 100 million years ago, the Earth didn't look the way it did today. Antarctica was joined to South America, Africa, there's India, Australia, New Zealand. But if we come forward in time, the sea opens up around Antarctica, and there's even a rift zone here in Western Antarctica. And eventually that ice or that continent becomes completely surrounded by ocean, and we developed a circumpolar current. And then ice began to form 34 million years ago, and West Antarctic formed 14 million years ago. So during this cooling off, several times in the last 5 million years, however, the West Antarctic ice sheet has disappeared, and we'll talk a little bit about that. So here's the temperature regime. Here are some of the reasons for the change in overall temperature, but the coming and going of glaciers on the order of about once every 100,000 years is a function of Earth's orbit around the sun and the irregularities in that. And so every 100,000 years, we get a buildup of ice, and then it catastrophically collapses. As you can imagine, it takes a long time to build up an ice sheet that gets as far south out of Canada as New York City. They collapse fairly fast. And if we go back 400,000 years ago, or even 100,000 years ago, there was less ice, and sea level was 4 to 6 meters higher than it is today. So when Antarctica became glaciated, what we had to do is develop an ice sheet. And that essentially means that there's more snow being deposited on Antarctica. It's cold enough, then melts the following year. And sorry, the typo, always one. The topography is buried, and it creates an ice dome. And the topography of Antarctica is high where there is a lot of ice, but there isn't necessarily land underneath that ice, and it flows slowly. And we'll look at this visualization of that, but you'll see the ice moving off of these high points and out towards the low points and out onto these ice shelves that are in red here. So let me see if I can go back to that, and we'll show you a different animation. So this is created from satellite imagery. They can track individual pieces of ice, and we could see the ice moving off of the top and moving down towards the ice shelves. And this is the West Antarctic ice sheet, and we're going to be talking about the Thwaites Glacier, which is this one here. This is the Ross Ice Shelf, where the McMurdo Station is, the big U.S. station in the southernmost end of Antarctica. But these ice streams have velocities up to 3.5 kilometers per year. The ice is moving very fast because a lot of ice has to make its way off Antarctica. All right. So how does ice move? How does all that ice get off of Antarctica? Imagine taking a spoon and dumping a bunch of porridge on a table, and then another spoon, and then dozens of spoons. Eventually, the blob would begin to slide off your table. And that's the same way with ice. We pile it up until it's past its strength and it deforms. And so here you have a person moving past ice that has material in it, and you can see how it's been folded into this shape. So most of the movement of ice in Antarctica is from the deformation of the ice crystals themselves. It also slides across the base of wet sediment underneath it. And in some places, in many places, Antarctic ice is underlain by water. There are lakes underneath the ice, and there is no friction, so it slides fairly easily across the water. The top 15, 20 meters will crack because it's not deep enough to be ductile and flow, and so you'll get crevasses as the lower parts deform and slide along the bottom. So when we look at a glacier, we can divide it into two zones. This is a cross section going from up high on the ice, like here on the Antarctic Peninsula, to somewhere down low where there's warmer air and lower elevation. And the upper 2/3 of the glacier is usually the accumulation zone. That's where you have a net gain of ice. So there's more snow every year than the melting of that snow at the base of the glacier or on top. And that ice and cold is exported downslope to an area where there is a net loss of ice every year. So there's less snow than there is melting, and that melting can be calving or the breaking off of ice out into to water in the ocean or a lake. It can sublimate off the top. It can melt at the bottom. All those together we call ablation. And so accumulation and ablation must be the same if the glacier is going to keep its position. If ablation is greater, the ice will retreat, the position of the snout will retreat, the ice keeps moving forward. And if there's more accumulation, it will move that way. And that's a function of lots of different things. Up on the Antarctic Peninsula, up in here, we have ice shelves, the Larsen ice shelves, and one of them collapsed in 1995. And in 2022, the Larsen B ice shelf collapsed, and the ice shelf retreated. I think it was almost 100 kilometers. And this, in and of itself, isn't changing sea level much or doing anything about other than taking away the ice shelf around Antarctica. But what's happening is that the tributaries to this basin are now speeding up because they've lost the buttressing of this large mass of ice at the bottom, at the end of their profile. Whoops, don't want to do that again. So this is an example of one of those. This is the Crane Glacier. When we lost the buttressing of the ice shelf, the ice behind it flowed faster. And since there was more leaving than coming in, that part had to get thin. And so when the glacier thins, the elevation or the accumulation zone gets smaller because that elevation now has moved up ice and we're getting less accumulation. And so not only is it thinning because of speeding up, there's going to be less accumulation. And so we begin an unwinding of the glacier. And here you see all the crevassing that's happening down at the base of the Crane Glacier, which was a tributary to the Larsen ice shelf. Okay, so much of the sensitivity of Antarctica is because it's composed of marine ice sheet. And a marine ice sheet overlies terrain that is largely below sea level. So if we look at the East Antarctic ice sheet, most of East Antarctica is above sea level, and anything that's blue here, light blue or dark blue, is below sea level, current sea level. The West Antarctic ice sheet over here, including the ice shelves, are mostly formed on land that is below sea level. This ice sheet started in the mountains, but the highest part of the ice sheet is actually over the deepest part of this rift basin from when Antarctica split off from the other continents. So if we look at this in cross-section, most of East Antarctic is above sea level here, 0, and then it terminates in some places there. But if we look on the West Antarctic ice sheet, in fact, most of it is on land that is below sea level. And the only reason the ice goes all the way to the bottom is that there's enough ice there, enough weight to keep it on the bottom. When we get the ice that's thin enough here out in the Ross ice shelf, it's floating. Okay? And look at the size of that. That's 700 kilometers. You'd have to drive from Lexington, Virginia to St. Louis before you got off that ice shelf, something like that. I asked my students this morning, how far is 700 kilometers? Okay, so you may have heard about Antarctica and the instability of marine ice sheets. The Thwaites Glacier has been nicknamed the Doomsday Glacier because it's one of the outlet glaciers for the West Antarctic ice sheet. And if it rapidly disappears, then it can sort of pull the rug out from underneath the West Antarctic ice sheet. Now, I'm a geologist, so my sense of time is wacky. And when I say quickly, that might mean over thousands of years. But there will be implications even of some melting for us in our lifetimes. So a marine ice sheet terminates in the ocean, and the land has an adverse slope. It's deeper underneath the main ice. And ocean currents can bring warm water in and melt the underside of the ice shelf, which thins it and it causes the ice to flow faster, which then thins the profile overall. And in most of the marine ice sheets in Antarctica, calving or the production of icebergs accounts for about half, and subsea melting accounts for the other half of ablation on these ice sheets. And that's typically, although we're beginning to get more surface melt, but it's not the biggest factor. And there's two settings in which ice terminates in water in Antarctica. In the Ross ice shelf, the marine ice sheet is very stable because the production of sea ice in that embayment and the strong winds that blow down off Antarctica there produce a really cold, salty water that circulates in here, and you can actually refreeze ice to the bottom of the ice shelf. So we can preserve that ice shelf. But if we go to the western side of Antarctica and look at the Thwaites Glacier, this warm seawater, a circumpolar deep water, is being forced over the edge of the continental shelf and can literally erode the bottom of the Thwaites Glacier, which then causes it to thin, and the grounding line where the glacier is not floating can then retreat. And once a glacier starts to float, it fractures and then moves faster. So this circumpolar current that developed 35 million years ago is really bringing a lot of warm water into this part of Antarctica, and it's producing a lot of this kind of marine ice sheet instability, and it's accounting for a huge amount of the overall melting in Antarctica. And so the Thwaites Glacier is really the poster child for what we need to know about how this works. And so scientists have been going at it for a decade and put a lot of effort into figuring out how this ice melts, what's the record of ice retreat across the bottom. These ROVs have been operating. They've drilled down in and put a lot of temperature sensors out in the shelf. And the reason for that is that we're losing a lot of ice in this part of Antarctica. A gigaton is a cubic kilometer of water. So that's 21 cubic kilometers of water per year, which is a big number. And if we look at all of Antarctica, some places are storing ice, but some places are losing a lot of ice, particularly the Antarctic Peninsula. And over here on the West Antarctic ice sheet, there's a few places in the east. But if we look at the mass balance for all of Antarctica and think how much scientific data that takes to do, we're losing 142 gigatons a year. A millimeter of sea level takes 350 or so. So we're about 40% of a millimeter is sea level rise is coming from Antarctica alone every year. Okay. And when we talk about melting ice and raising sea level, all of this ice isn't raising sea level because here's the sea and some of the ice is below sea level. So that wouldn't count. And then ice is buoyant. So we got to go up another 10%. And there's a little bit of air in ice. So that doesn't count. But this gray area is the ice that contributes to sea level. And I urge you to go find out how much your favorite glacier could contribute to sea level. All right. Sea level change. Okay. We talk about it in millimeters and centimeters per year. And if you live on the coast, you might think, sea level rise of a centimeter or an inch. What does that mean? But if we look at the slope of the shelf off of the North Carolina coast, for example, we can get the slope of that shelf, and it's, I think, about 50 meters in 90 kilometers. And as sea level has risen over time, you can see some older barrier islands down in here. If the barrier island wants to survive sea level rise, it has to move backwards up that slope. Sea level rise currently is about 3.5 millimeters per year. Most of that is warming of the ocean, but ice melting is approaching 1 millimeter of that sea level rise. And if we think about the mortgage on a house that you buy on the coast, say 30 years, 30 years times 3.3 millimeters is a 10 centimeter rise. That's 180 meters of movement of that shoreline. Remember back to the last time you went to the beach, and you think about you're about 3 houses back, and that's just in 30 years. So we're in for some changes if sea level keeps up its current rate of rise. So thanks for your attention. I think Antarctica is an important place, a place that deserves lots of scientific study, and it's getting it because it's going to be critical for our habitation of the coastal areas. So Mike, I'm going to stop and give it over to you.
Okay, just give me a second here to get my screen up. Oops. Okay. So is my screen up there or not? No, I don't think it is.
Yeah, see your face, Mike. That's it.
Okay, just a second. Share screen. And I think. Second, I just need to go and do this. Okay. Is that working?
That works.
Okay. So I'm on the West Coast and I'm Canadian, so I will be using metric system. But I wanted to share with you some thoughts about Antarctica and what I've seen. And again, just to give you a little bit of kind of the geography here. Just 1 second, I need to minimize that. So you can see here the area that most people visit is the Antarctic Peninsula, which is that section in the top left-hand corner, Graham Land, and that's the area where most visitors and most of the wildlife is, to be honest. So again, another couple of views of that. And I think one of the things that I find from a geological point of view very interesting is you can really see how the Scotia Plate has pushed its way between South America and the Antarctic Peninsula, leaving behind places like South Georgia and the South Shetlands. So I was going to talk a little bit about the difference between land ice and sea ice, and then talk a little bit about icebergs, and then a bit more about sea ice and how it changes, and also about a program called the Extreme Ice Survey. So first of all, you can divide the ice in Antarctica into land ice and sea ice. And David was basically talking about land ice, which is the glacial ice, the stuff that makes up all the ice sheets and the glaciers. And that is what gives rise to icebergs when they calve off. Sea ice, however, is frozen seawater, and it typically forms every winter and melts back every summer. And as David mentioned, we've got shelf ice. There is a huge amount of shelf ice. The blue, kind of turquoisey blue areas are the shelf ice here. The biggest one would be the Ross ice shelf and the Ronne-Filchner ice shelf on the upper section there. So there we go. You can see kind of the major ice sheets of Antarctica. And when you look at the edge of an ice sheet, you're looking often at 1,000 feet, 300 meters of ice. And of that, about 30 meters or 100 feet is above sea level. And I think David showed a similar diagram to this. And there are many, many kinds of icebergs. But the most spectacular ones are what we call the tabular icebergs, and they are the ones that break off the ice shelves. And to be called a tabular iceberg, it's supposed to be like 5 times as long as they're thick. And here's a picture of a small tabular iceberg. And you can see it does look a bit like a table, very flat on top. And these have all broken off a ice sheet. The largest reported iceberg was reported in 1956, 31,000 square kilometers, larger than Belgium or Maryland. So it's huge. And all of the large icebergs get named. If they're longer or bigger than 10 nautical miles, which is about 11 and a half statute miles, they get a name. And the name begins with what we call a quadrant. There's the A quadrant, the B quadrant, the C quadrant, and the D quadrant. And because you've got the Ross ice shelf is primarily in B and the Ronne ice shelf is in A, a lot of the icebergs that we see are either A or B. The largest named iceberg formed in 2001 was B15. And so the number is basically the order in which that iceberg broke off. So B15 started in 2001, and you can kind of see its movement around the coast. So icebergs typically will break off in an ice shelf, and then they will migrate around the coast of Antarctica through the Weddell Sea and then off into the South Atlantic. And there's a map showing you all those red lines are essentially the tracks of icebergs. So you can see the vast majority of those icebergs are kind of cruising around the coast of Antarctica and then heading off into the Atlantic. I wanted to just point out that there was 2 icebergs. These are the 2 furthest north reported icebergs. They're basically almost at the level of Santiago, Chile and Buenos Aires. So they were able to move a long way north before they finally melted away. Oops, sorry. Okay. Here's another view of a largish tabular iceberg seen from the National Geographic Explorer. And I wanted to tell you a little bit about one particular iceberg, the A68 iceberg. And in 2017, that iceberg started to break apart. And you can see here it cracked off. And you can see the scale here, 20 kilometers. So this was well over 150 kilometers long. And the thickness, typically about 190 meters, or in this case, 620 feet or so. I wanted to show you, this is a satellite image, and we use satellite images for ice navigation in Antarctica. The bluish color is land, and the various grays are ice and so on. But if you notice here, that is the South Shetland Islands. This is James Ross Island, one of the larger islands on the peninsula. And that chunk there is actually A68A. So it's actually bigger than most of the islands in the Antarctic Peninsula area. And you can see it basically broke off and then made its way towards South Georgia. Here's a satellite image showing you A68A approaching South Georgia. And this is November, December of 2020. And again, you can see its path there. What's interesting is that it basically hit the continental shelf or the shelf of South Georgia and then started to break apart. And here you can see the fragments. And this next diagram shows you a bit of an alphabet soup because A68 broke into many chunks, all of which were bigger than 10 nautical miles. So they all got names before they melted away. This one here you may have heard of in the news. This one, again, broke off in 2011 and then basically got going in March of 2022. And it's twice the size of Greater London. And in August of this year, it was still spinning around near the South Orkney Islands. But now I want to switch from icebergs, which are kind of the most dramatic ice that you see as you visit the Antarctic, into the sea ice. And pretty much all the data that we see shows a decreasing amount of sea ice. Also, this last season, I was in Antarctica this last season, the 23-24 season, and I noticed a lot more icebergs out in the ocean. And I suspect that that means that more of them were, or I should say, there weren't as many that were trapped in the sea ice. So what is sea ice? It forms when the water temperatures go below negative 1.8 Celsius. It's very low profile, and it forms two main types, what we call pack ice, which is drifting ice, and fast ice, which is connected to land. And here's just a few pictures. You can see that it forms like little pancakes on the surface, and then they glue themselves together. You start to get pancake ice like this, and then you can see large patches of ice. And this is in breakup in the spring. But the sea ice is very important to a lot of the wildlife. These are a bunch of crab-eater seals, and they are hanging around on the nice flat ice because it's very easy for them to clamber onto. A regular iceberg would be very difficult, but sea ice is easy. And typically, sea ice is not much thicker than a couple of meters. The next few slides that I want to share with you show sea ice extent at different times of year and in different years. So the first picture is 1999, and September 99. September is typically the largest extent, and February is the least extent. And I want to point out that that yellow line is the 1979 to 2000 median. And what you'll notice here is that in all of these diagrams, the ice does not come out to those levels. This was 2020. You can see again the ice, especially in the summer, so the peak of summer is February. That would be the equivalent to our August. You can see that all of the ice, or a large amount of the ice in both the Weddell Sea and the Ross Sea, has melted back. This one here, fairly recent, you can see September 2024. It really doesn't, there's some huge gaps since the 81 to 2010 average. And then so there's September again. And just to show you some graphs, the dotted line there is the 1981 to 2020 average. And in 2017, there was a record low. It was a little bit higher in 2020 and 2021, but still below the average. And again, in 2023, this was followed with a new record low. And I just thought I would share this graph here showing you the August. So that's kind of winter time, relatively steady for a long time, but then recently it seems to have taken a bit of a decline. And then this is the February. So that slide was August. So that's winter time. This is summertime. And notice that in the last few years, since 2020, there's been a dramatic decline in the amount of sea ice. And again, just another graph, 2024 and 2023 versus that gray line. This is showing you the amount of ice at various times. And again, recent data, much, much less ice. And again, just another graph showing you the same thing. So what does that mean for wildlife? Well, most Antarctic wildlife depends on the sea ice because the sea ice is home to the phytoplankton, which feeds the krill, which feeds the penguins and the whales and so on. The next thing I wanted to share with you briefly is a program called the Extreme Ice Survey. And the Extreme Ice Survey is a program that was set up by James Balog to look at glaciers around the world. And there are these little cameras scattered around the Antarctic Peninsula. I had the good fortune of helping to service one of these a few years ago. And first of all, we had to climb up this little ravine and make our way up to the top of this hill. And you can see this is the National Geographic Explorer. And the Explorer is a ship that actually services many of these cameras around the Antarctic. Over here, you can see one of the camera setups. There's a big battery box, a solar panel, and the two cameras. And the idea is that these cameras take a picture of the glacier every hour during daylight. And so they're basically recording the movement of the glaciers. Just a couple more views. And then every year we try to get in and check the batteries, check the cards, download the data, and then move on. And here you can see myself checking one of the cameras. If you look at that hillside in a place called Sierra Cove on the Antarctic Peninsula, you probably can't see the camera. The camera's in that little red circle, and zooming in a little bit more, you might be able to see that camera now. And there we go. Again, you can see the camera in the hillside. And so, as I said, these cameras are observing glacial change. And this next diagram is actually satellite imagery of the glaciers in Sierra Cove. And Sierra Cove is one of the few glaciers in the peninsula that does not seem to, or these glaciers, the Gregory and Brabant, Brigade rather, glaciers, don't seem to be moving significantly in that period of time. And I wanted to share with you, I don't know if this will work here. Hopefully it'll start moving here. So these are just a time lapse of images taken by those extreme ice cameras. And you can really see how the glacier is constantly moving downhill, constantly falling off or breaking off icebergs. And you can see that this particular glacier has not changed dramatically. Around the world, there's 43 time-lapse cameras. And the data on the Antarctic shows that out of 244 glaciers that have been studied in the Antarctic, 87% of them are in retreat and 13 are advancing. So why, might you ask, are some of them advancing? Well, as it warms, you can actually get more snow. And in some areas on the west side, you can get more snow piling in, and that can actually add to the accumulation zone. And I just thought I would show, this is where the various stations are in the Antarctic Peninsula. Nico Harbor, Sierra Cove, and Brown Bluff are all common visitor sites. And I think now we are ready for some questions. I'm going to stop sharing if I can figure out how to do that. There we go.
Mike, maybe I'll start off by asking you a question. So you usually travel in the austral summertime, of course.
Correct.
And if you see less ice, is that because there's less sea ice or there's less iceberg production from the ends of the glaciers?
What I'm really noticing is less sea ice. So places that were very difficult to get to in 2017 are now quite easy to get to with, through the ice. But I think an interesting kind of side effect is that a lot of those icebergs that you showed in your images, in the satellite images, are trapped typically in the sea ice, and they can be trapped for decades in that sea ice. As that sea ice starts to melt, then those icebergs are suddenly free to go. And that's why I think we're seeing kind of an increased number of these large tabular icebergs heading out.
Yeah, I believe it's the word melange. Is that what they use for that sort of refrozen mass of iceberg and sea ice?
Yeah.
Yeah, great. Thank you. Any questions for me?
I was going to ask with your presentation there, the data that you're showing there is all coming from satellites, and I think it's so important to realize how important satellites are for measuring what's going on, because we can't see this ourselves. It's even the mass loss is all done by satellite. And
Correct.
I guess, I think it's not really a question, but more of an observation, I guess, that
Right, and there was some gaps in that plot, and that was the loss of I think it's called the GRACE satellites, and they do that by measuring the gravity. Two satellites that can sense the gravity, so they know how much mass is underneath them. So it's really a fantastic science, but we do need those data.
Yeah.
All right, I'm going to open up the floor for questions from the audience. Just a reminder, if you have questions, please feel free to enter it in the Q&A that you'll find at the bottom of your screen. So, Dave, this question is from you. It's coming in from Jesse. I would be interested to hear Dave speak more about how relatively small sea level rises will affect current shoreline profiles.
Oh, okay. Yeah. Switching into my coastal geologist hat. Yeah, Jesse, that's an excellent question. Thanks for asking. Yeah, the slope of the coast is the critical thing. So if you're on the coast of Maine on a rocky coast and it gets deep offshore, sea level rise is not a problem. But if you're on a delta, say some of the larger Asian cities that we have built on the deltas of the big rivers, the slopes are incredibly low, like the one I showed. And so a small movement of sea level actually pushes the shoreline a big distance. And you can ask the Dutch about how hard they had to work to keep the sea out of their low sloping coastline. But it is the slope of the coast that is the main question. So if you're on the coast, look at your slope. Ruth, you're muted.
If I had a penny for every time I've heard that since the pandemic. All right, I apologize. I'm going to begin again. I think this one might be for either one of you. The question is, are the ice shelves more inland, such as at the South Pole, thinning or thickening?
Mike?
It's my understanding that overall things are thinning. However, the biggest changes are at the outside edges.
Great, thank you. So this is coming in from Matt Tuckler. Thank you. Will the ground that is below sea level and on which these huge sheets are sitting get higher once the ice melts?
Good question, Matt. Yes, isostatic rebound. So when you take a weight off of the Earth, it is being flexually supported by the ductile mantle, and it will pop back. And so when you remove an ice sheet, you do get some elevation back. So again, you're displacing sea. So that's a problem because you're pushing the sea out to somewhere else. But West Antarctica in particular is on some very weak, hot crust. So I believe they think the isostatic rebound of the crust might happen within decades of loss of the ice. And so it wouldn't be under sea level anymore. So in the next ice age, it could grow again.
Yeah, I often refer to this effect as the mattress effect, where if you sit on a mattress, it depresses, and when you get off it, it comes back up again. And that's what happens with ice.
But it's an old mattress that takes a week for it to come back up.
A little bit slower.
We're gonna go back to sea level rise. So what is your estimate of sea level rise on the mid-Atlantic East Coast in the next 10 years?
In the next 10 years, I would extrapolate from what's happening now, and then I would potentially add more because we're increasing the rate of ice melting in Antarctica and temperatures are not going down. They're going up faster. But, glacial or sea level is a complicated thing. And so if we go to tidewater down by Norfolk, the effect of sea level rise in Norfolk is actually greater than it is in much of the rest of the mid-Atlantic coast because Norfolk is subsiding a little bit in addition to the sea level rise. And so it's already encroaching on streets and parking lots during king tides, during normal highest high tides of the year. And so every place has its own details depending on geology or what's happening at the coast. In some places, we're withdrawing groundwater or oil and gas, and the earth is subsiding because of that, and sea level exacerbated by that as well. So I think sea level will rise, barrier islands will retreat, coastal areas will be flooded. It's happening now and it doesn't seem like it's slowing down.
Thank you, Dave. So this one comes into Rob. Thank you. As ice melt continues to increase, will the rising temperature of the sea due to carbon absorption hasten the rate of seasonal melt?
So let's see. Yes, carbon is absorbed in the sea, but that's not what is increasing its temperature. That's just because it's surrounded by warmer air. But that's where a lot of the CO2 that we put in the atmosphere has gone, luckily. Although if you ask the coral, they're not very happy about that because as we absorb more CO2, the ocean gets more acidic, and pretty soon all the sea life that uses calcium carbonate to make their shells won't be able to do it. And so they will cease to exist. So we don't want to raise CO2 in the ocean too much. But there's a lot of positive feedback that's happening in glacial melting that as sea level rises and as glaciers thin and there's more current coming in, the glaciers melt faster and they get thinner. And then we expose more of the shoreline to sun, which absorbs more heat. And there's less sea ice, as Mike said. And so then we get this positive feedback and runaway freight train. And in geologic time, it took 100,000 years to make an ice sheet in North America. It took about 8 to get rid of it. So it works to build ice, but they collapse fast. So, and again, that's on a geologist talking, but we are on the positive feedback runaway freight train of ice loss in Antarctica.
Thank you. Mike, this one is for you. During your expeditions, what changes have you observed in the wildlife and ecosystems of Antarctica due to climate change?
It is hard to tease out climate change in the changes. And I've been going to Antarctica since 2017 only, but I've noticed one change, certainly in the last couple of years, which are crab-eater seals appear way less common around the peninsula. and they are seals that really like to spend time on sea ice. And I think that that is likely associated with a decrease in sea ice. And that would certainly be, to me, a change in the wildlife. We're also seeing penguin colonies, particularly the emperor penguin colonies, being threatened by basically the ice that the chicks are. So the emperor penguins nest on sea ice that is far, far away from the coast, and then usually by the time that ice melts, the chicks have already fledged and left. But we're seeing now that as that sea ice that sea ice melt is happening sooner, the chicks are not fully fledged. I definitely saw that in the Weddell Sea this past winter.
Discouraging. So this question's coming in from Corey. Thank you. Is there anything we could do or not do about the ice melt in Antarctica?
That's a matter of debate among glaciologists. There was actually an interesting article just published in the Atlantic in the last few months about what some would say some rogue glaciologists who have the idea that if the water underneath glaciers helps them move faster and we want to keep it there, what we want to do is stick it to the ground underneath by pumping out all the water. So he's proposed that instead of worrying about it, we should just go dehydrate the glacier bottoms in the West Antarctic. And there's a lot of natural data that says when the water's there, glaciers move faster, and when it disappears, they slow down. And so it's based on good science, but the technological challenge of that is extraordinary.
Thank you. I think we've got a lot of concern over our East Coast. So what is the outlook for the Outer Banks over the next 50 years?
I wouldn't buy a house on the beach right now. That's my outlook. And, we are, as a society, ensuring and protecting and taking care of those people out on the Outer Banks. And so as Orrin Pilkey, who's a famous coastal geologist from Duke's, said that, you should have your time at the beach, but then you should move to the back of the row. And then as the barrier island rolls back every hurricane, that you'd eventually, some generation down the line, would be back at the beachfront. And so you just take your turn at the front and then you move to the back of the line. But we're more interested in protecting the coast, but what that will eventually do is lose all the sand offshore and the barrier islands will be drowned.
So this question is for both of you. How can the public better understand the implications of ice melt, and what actions can individuals take to contribute to climate solutions?
My answer is that the more people understand about the science of climate change, the more people will be able to act to change their behavior to help slow things down. And it's a slow process.
Agreed. Yeah, I think there's a lot of information out there that's available. A lot of excellent work is being done with your public tax dollars all around the world. And you should read it. And it is motivating to change the way our economy works and to change the way we do things so that we might avoid some of the worst problems with rising sea level and temperature and et cetera.
Thank you. This question is from Evan. At the current rate of ice melt, when do you estimate all sea ice and land ice will be gone?
Well, I could say about the sea ice. I think sea ice will, because sea ice forms every winter and then melts back every summer, it should be around for a long time. Just it may not get out as far, and it's going to melt back further every year. We're seeing that both in the Antarctic and also in the Arctic. But putting a time, I have no idea.
It would be hard to put a time on how long it would take to melt the Antarctic. 90% of the world's fresh water is on the Antarctic continent as ice, and it is in a cold place with a mean annual temperature well below zero. So it's going to take a while, a geologically long time to get rid of all the ice, but we don't need to get rid of all the ice. There's what, 50 meters worth of sea, 35 meters worth of sea level rise there. That would be a catastrophe, but that's going to take thousands, if not tens or hundreds of thousands of years to undo what 35 million years of ice collection has done. So we're safe for now, but again, that 0.5 millimeter is a big deal, and we're doing that now. We are losing a 0.5 millimeter a year from ice from Antarctica easily, and that can grow.
We've got time for a couple more questions. Are there other areas around the globe where we are seeing glaciers advancing versus retreating, aside from those in East Antarctica? And if so, is that mostly due to changing weather patterns resulting in more precipitation?
Yes, there are glaciers that are growing, and there are places where we're getting more accumulation than ablation. Warmer air holds more water, so we expect more precipitation on the coastal regions of our ice sheets and in some locations, but the ablation is also increasing, and it's the balance of those two. So we will see, like Mike showed, some glaciers advance because of the growth of snowfall. Ice or the coldest air doesn't hold much moisture. It doesn't contribute to accumulation, but as it warms, it can pick up more water from the sea and dump it on the land. And there will be locations, but I guess it's that you have to worry about the trend of all the glaciers and not just the anomalies that are growing.
I think, if I remember correctly, it's something like 97% of glaciers worldwide are in retreat, and I think only 3% are in advance. I have really noticed traveling in both South Georgia and in Patagonia, multiple 100-meter retreats in a matter of years. And looking at the satellite images, you can see in a decade several kilometers of retreat on many of these glaciers. So there's no question that around the globe we've got glaciers retreating everywhere, except for just a handful.
All right, we're going to take one more question. This is from Barbara. Thank you. Will the changes in ice impact ocean current circulation?
Oh, that's a great question, Barbara. In fact, yes, because the development of ice in Antarctica and the melting of that ice was a large part of what helped produce the deep water currents that we have around the whole globe. And currently, what we're seeing for tropical air masses, everybody's heard of El Nino and La Nina. Those cycles are showing up in Antarctica. So there are these teleconnections between Antarctica and other coastal and atmospheric conditions around the world, and other conditions around the world have an important impact in Antarctica. So the sea connects us all, and a change in one place generally means you're going to see a change somewhere else.
Thank you. think that's a wrap for tonight. Thank you all for being with us this evening and for such great questions. A heartfelt thank you to our speakers, Professor Dave Harbour and Mike Jackson, for sharing their perspectives on the science of ice melt and its significant implications for our planet. For those of you joining WNL's Antarctica journey this January, you are in for a treat. I'm excited to share that both Professor Harbour will be our faculty host and Mike Jackson will also be there as an expedition leader. This trip sold out quickly. Many of you are on the wait list. We appreciate the enthusiasm. We anticipate offering this program again in 2027. So please feel free to reach out to our lifelong learning team if you're interested in learning more. Again, thanks for your participation, and we look forward to seeing you at future events. Have a great night, everybody.
Good night.
Good night.